to this 20 governing equations. So the equations, for example, our form. So first we will start with the conservation of mass. So conservation of mass equation in integral form gives us that volumetric integral of del rho by del t plus surface integral of v vector dot ds vector is equal to 0. So this is something which is the integral form of continuity equation. Now particularly this term over here, using the Gauss divergence theorem, this surface integral can be converted into volume integral. So if we do so, sorry, one mistake I have done, it should be rho v vector dot ds. Now this particular term, second term, so first term is having volume integral, so another issue is it should have integral over v bar also. Okay, so first term is in volume integral. So what I want my entire equation in the volume integral. So for the second term also I will try to convert it into the volume integral. Okay, so if I do so, I will get the replacement for this term in terms of volume integral will become volume integral v bar, and this rho v vector dot ds will become divergence of rho v vector into dv bar. Okay, so this is the conversion from surface integral to the volume integral. So now if I write, then this first term is also volume integral, second term is also volume integral. So ultimately this dv bar I can take outside and everything I can write as a single volume integral. So it will be becoming del rho by del t plus divergence of rho v vector and whole integral over the dv bar is equal to 0. Okay, so this is something which we are actually getting over here. Now the point is because this particular equation is equal to 0, so whenever we try to use this dv bar, so basically what we consider, if say this is the point at which I want to apply over the continuity equation, so around this point I take a small differential element. So I take a small differential element which is having volume dv bar. Okay, and this element is such that within this element my variation of property is not there, so rho is almost constant within this element. So that is basically the assumption over here. So now what I can do, ultimately the size of this element dv bar cannot be 0. Okay, so dv bar, sorry, not vector, this should be v bar. So ultimately the size of this vector dv bar, this cannot be 0. As it cannot be 0, so ultimately this integrand has to be 0, then only my equation will be satisfying. Okay, so then I can say that del rho by del t plus divergence of rho v vector is equal to 0. So this is, now if you see this particular equation, is purely in the differential form. So I can say that this is the differential form of continuity equation. More importantly, whatever the form we have derived over here, this particular form is also called as the conservative form of continuity equation. Okay, so this is also called as conservative form of continuity equation. Okay, so now here basically this particular form is applicable for a control volume which is fixed in space. So here you are having this control volume which is fixed in space, and within this there is variation because of the time as well as variation because of the spatial coordinates. So that is taken care by del operator, which is equal to del by del x I cap plus del by del y j cap plus del by del z k cap. Okay, so this is our del operator over here. Now, so this is, I have written the continuity equation in conservative form. Okay. Similarly, I can also write down the momentum equation. Okay. So if I go for momentum equation, what we have, we know that integral form of the momentum equation is volume integral of del rho v vector by del t plus into dv bar plus surface integral of rho v vector dot ds vector times v vector, that is equal to minus surface integral of p into ds vector. Okay, and for compressible flow analysis, viscosity is negligible. If I consider the body force, then I will be having volume integral of rho f vector into dv bar. Okay, so this is my body force term over here. Okay, so similarly, what I will do now, these two surface integrals I will try to convert into a volumetric integral. So if I do so, my equation will become volumetric integral of, okay, so before that, let's also do one thing, because momentum equation we will be having actually separately for x coordinate, y coordinate and z coordinate. So that's why I will try to write individually over here. So if I have to write x momentum equation, then I can write over here del rho x component of velocity vx divided by del t into dv bar plus surface integral of, so this is my x component of momentum equation. So let me first write x component, then I will use the transformation from surface integral to volume integral. Okay, so this will be becoming surface integral of rho v vector dot ds vector times vx, then pressure will remain, pressure force will remain the same, and body force will become, because here this will be uh, okay, so volume integral of rho fx, here also I should write actually px, so basically pressure in x direction only. Okay, or in other way, pressure will be always the say same, so I can write this area I will be basically considering in x direction. Okay, so this rho fx into dv bar. Okay, so now let me convert these surface integrals into the volume integrals. So if I do so, now I can write, first is my volume integral only, so del rho vx by del t into dv bar plus this will become now volume integral, and I will get divergence of rho v vector into vx, and this integration will be over dv bar. And this, now here this pressure force I have to consider only in x direction, so first I am writing it as a volume integral. Now if you see, I am using the divergence operator. Okay, so for this pressure term I want to use only the pressure force in x direction, so that's why this del is having three components, del by del x I cap plus del by del y j cap plus del by del z k cap. I will choose only the x component of this. So x component is del by del x, so I will be writing del p by del x into dv bar. Okay, and third component is already in the volume integral, so rho fx into dv bar. Okay, so now what I can do, I can bring all the terms on the single side and put inside a single volumetric integral. So this is how my volumetric integral of del rho vx by del t plus divergence of rho v vector into vx, pressure will become plus del p by del x, and this body force will become minus rho fx, and this whole dv bar equal to 0. So once again, if this integration has to be 0, so only this integrand must be 0, because this particular dv bar is actually finite in size. Okay, even if it is infinitesimally small, but it is not exactly equal to 0. So now this thing I have to put integrand equal to 0. So if I put integrand equal to 0, finally I will get rho del rho vx by del t plus divergence of rho v vector into vx equal to minus del p by del x plus rho into fx. So this is nothing but my continued momentum equation in differential form in x direction. Okay, similarly, now I need not to do whole analysis for y. I can just, using this equation, I can write the making the analogy, I can write y momentum equation. So y momentum equation will become del rho vy by del t plus divergence of rho v vector into vy, and then I will be having minus del p by del y plus rho into fy. Okay, so then I will be having z momentum equation, so that will be becoming del rho vz by del t plus divergence of rho v vector into vz equal to minus del p by del z plus rho fz. Okay, so this is differential form, and these particular forms are nothing but the conservative forms of momentum equations. So these are called as conservative forms of momentum equation. Okay, then now what I can do, if I have to write this particular equation in vector form, so in vector form basically I can combine all the x, y and z equations. So my first term will become del by del t of rho. Now I have to write in vector form. So individual component was vx, vy, vz. So in vector form it will be a velocity v vector plus divergence of rho v vector, and this also individual components will become actually v vector over here, and then this will become gradient of p, because all the pressures in xyz has to come into a single term, so it will be becoming gradient of p plus rho times f vector. So fx, fy, fz were the components. So this is nothing but my momentum equation in vector form. Okay, and this is the differential form of momentum equation. Now similarly I can write down the energy equation. So for energy equation also, what I will do, I will first start from the uh, integral form of the energy equation. So integral form of the energy equation says that volume integral del by del t rho u plus v square by 2 into dv bar plus surface integral of rho v vector dot ds vector times u plus v square by 2. Okay, so this is the left hand side, and in the right hand side I will be having first term, say because of the heat generation. So because of the heat generation it will be and here this has to be, okay, ds I have already written. Say if q dot is volumetric heat generation, then rate of heat generation per unit volume, then v bar sorry, per unit mass, so then it will be dv bar. Okay, and now this is the heat generation term. Then next will be the due to pressure force work term. So that will be surface integral of pressure v vector dot ds vector. Okay, this is the, then I will be having some term due to body force. So body force, it will be rho f vector dot v vector into integral dv bar. Okay, so this is my energy equation in integral form. Now you might be surprised to know that I have not taken some of the forms, because particularly I am writing the energy equation which is useful for compressible flow analysis. So for compressible flow analysis, as we are not considering the viscous dissipation and the irreversible effects, that's why conduction term and viscous forces term I have not considered over here. Okay, so now once again my objective is to convert this surface integral terms into volumetric integral terms. So del by del t of rho times u plus v square by 2 dv bar, this is volumetric integral, plus this will be becoming divergence of, okay, so rho v vector dot ds vector into u plus v square by 2. Okay, so this will be the second term, and here also now I will be having volumetric integral dv bar. Okay, then I will be having here volumetric integral of rho q dot into dv bar minus surface integral of rho v vector, sorry, now this I have to convert into volumetric integral. So I will take here one more integral term, then v bar, and it will be becoming divergence of p into v vector, okay, dv bar, and last term is in the volumetric integral only. Okay, so then now I will omit some of the steps. So next step is we have to put all these terms on one side and then take integral over dv bar, and that then integrand will be becoming equal to 0. So that step I am not doing over here. So ultimately if I do that, then I will be getting my final equation as del by del t of rho times uh, u plus v square by 2 plus divergence of rho v vector, sorry, here this is wrongly written, ds will not come because I have converted the integral from surface to volume. Okay, so this will be rho v vector into u plus v square by 2, and that will be equal to rho q dot minus divergence of p v vector plus rho f vector dot v vector. So this is my differential form of energy equation. Okay, okay, so this is my differential form of energy equation. Now what we can do, so one important point in the previous discussion when I discussed about the momentum equation, so in these momentum equations I have not taken the viscous term. So these particular momentum equations are popularly known as Euler's equation. These are popularly known as Euler's equation. And over here this is the differential form of energy equation, and once again this is also the conservative form. So conservative form of energy equation. So all these three equations like continuity, momentum and energy, which I have derived over here, these are applicable for a small sized control volume which is actually fixed in space. So this is not moving, this is fixed in space, but across this control volume fluid is flowing, and that fluid can have variations due to two factors. One is variation due to time and another is variation due to spatial parameters in the flow field. Okay, so that is something which I have actually done over here. So this is differential form of energy equation, and it is also called as conservative form. So basically the reason these all three equations are called the conservative form is that because integral form is based on the conservation principle, like we are making conservation of the quantities for a finite sized control volume. So as these equations are derived from the conservative form, that's why these are also called as conservative form of equation. Second perspective of looking into this factor is that particularly comes from the study of computational fluid dynamics. So basically conservative and non-conservative forms are mainly comes in the nomenclature of computational fluid dynamics due to certain issues in the numerical solution of the equations. Okay, so the terms which are having divergence of rho v vector, divergence of rho v vector and divergence of rho v vector into u plus v square by 2. Okay, so when the complete term is inside the del operator, so this is in continuity equation, this is in momentum equation, and this is in energy equation. So when I have complete flow field term inside the del operator, so del operator is being applied to the complete term, then particularly we call the equations as nothing but the conservative form. Okay, and another important aspect is because in these equations this particular term takes care of the variation due to spatial parameters, and this term takes care of the variation due to time parameters. Okay, so and as these all these three equations are applicable for a fixed control volume. Okay, so which is fixed in space and flow is moving across it. So this is the reason sometimes these are also known as Eulerian form of equations. But important point is don't confuse with the Euler equation. Euler equation is only specific to the momentum equation when we are not considering the viscous term. Okay, so then whatever our momentum equation is, that is called as Euler's equation. So that particularly comes from the name of the scientist, and this Eulerian form of equation comes from the physical understanding that if our control volume is fixed in space and we are having flow across the control volume, and in that particular control volume we are studying the variation because of the spatial parameters and the time parameter, then we call as the Eulerian form. Okay, so it means we are having fixed in space. For example, in our basic fluid mechanics course we see that if our control volume is fixed in space, then we say that it is nothing but the Euler treatment of the flow field. And if our fluid element is moving with the is moving along a streamline, moving with the flow, then we call that as nothing but the Lagrangian treatment of the flow field. Okay, so we have seen the conservative forms or the Eulerian form of equations for continuity, momentum and energy equations, and we have converted these equations from integral to the differential form. Okay, now let's also try to see the non-conservative form of equations. So in case of non-conservative form, first I will write the conservative form of say continuity equation. So that is del rho by del t plus divergence of rho v vector, and that is equal to 0. Okay, so ultimately what I am doing, I can now use the vector calculus and I can take this differential separately. So I can write plus rho times divergence of v vector plus v vector times gradient of rho. this is equal to 0. Okay, so this is something which I can write over here. Now before making, so here I have to make some analogy. So before making that analogy, let me introduce you to one more small topic. So say I have one fluid element, okay, and this fluid element is initially at some location 1, okay, and at this location its coordinates are x1, y1 and z1. Now this fluid element is moving in some flow field and it has reached to some other location to where its coordinates are x2, y2 and z2, okay, and let's say at this location it was at time t1 and at this location it is at time t2, okay. Now inside this flow field, here density is rho1 and here density is rho2, okay. So as x, y, z and time all are changing, so ultimately my variation in density will be function of x, y, z and t. Fine. Now these two locations are fixed over here and I know the corresponding x and y coordinates. So what I can do, I can take the help of Taylor's series expansion, and by using the Taylor series what I can do, basically I can find out the density at point 2 as the function of density at point 1, okay. So that if I do, I can write rho 2 will be equal to rho 1 plus del rho by del x into x2 minus x1 plus del rho by del y into y2 minus y1 plus del rho by del z into z2 minus z1 plus del rho by del t into t2 minus t1. So from here I can simply write that rho 2 minus rho 1, so rho 1 I am taking to left hand side, and another thing I am doing is I am dividing this whole equation with t2 minus t1. So this will become del rho by del x into x2 minus x1 by t2 minus t1 plus del rho by del y into y2 minus y1 by t2 minus t1 plus del rho by del z into z2 minus z1 by t2 minus t1 plus del rho by del t, okay. Now till now what I was having actually finite change in time. So basically t1 and t2 were having some finite change. Now if I consider my situation such that t2 is approaching to t1, if t2 is approaching to t1, then I can take the limit and I can write limit t2 approaching to t1 rho 2 minus rho 1 divided by t2 minus t1. So this is nothing but the definition of a derivative, instantaneous derivative or total derivative. So what I can do, I can write this as nothing but d rho by dt. Fine. Similarly, limit of t2 approaches to t1 into x2 minus x1 by t2 minus t1 will become nothing but instantaneous velocity in x direction. So that I can write as Vx. Okay. So likewise, my whole equation will become d rho by dt equal to Vx times del rho by del x plus Vy times del rho by del y plus Vz times del rho by del z plus del rho by del t. Is this thing clear? Now we know that V vector will be equal to Vx I cap plus Vy j cap plus Vz k cap, and del operator will be del by del x I plus del by del y j plus del by del y k. So using this formulation, I can write in vector notation that it will be v vector times gradient of rho. Fine. V vector times gradient of rho plus del rho by del t. Okay. Is this point clear? Now the way I have written it for property density, similarly I can write it for other properties such as temperature. So if I have to write temperature, then for temperature it will be becoming dt by dt equal to v vector dot gradient of temperature plus del t by del t. Okay. So the term on the left hand side is called as total derivative. This is called as total derivative. And this particular term is called as convective term, and this particular term is called as local term. Okay. So physically you have to understand, let's consider that we have outside a winter season. Okay. So in case of winter season, say outside temperature is 10 degrees Celsius and this particular room is air conditioned. And so what will be happening if you are outside? So outside you will be feeling a temperature of 10 degrees Celsius and this room is heated and it is maintained at say 25 degrees Celsius. So whenever you enter through the door and you come from outside to inside, you will be finding a temperature change and you will be feeling a temperature of 25 degrees Celsius. So basically what you have done, you have changed your location from outside to inside and then you have felt a temperature change. So it means that this is nothing but over here del by del x, del by del y or del by del z. So these are the terms which are associated to the change of location. Okay, over here it is given by v vector dot gradient of t. So it means that whatever temperature change you will be experiencing, that temperature change can be explained by this convective term. Now let's consider another situation, that at this particular door we are having one blower of hot air also. Okay, so there is a one blower of hot air at the top and that is giving hot air from say top to down. It is flowing with say some fan of high velocity. Okay, so whenever you are entering from outside to inside, obviously you have to cross through that door and at that door there is some blower of the air which is throwing hot air. So momentarily what will be happening? You will be finding the instant when you are entering through the door, you will be feeling the hotness or you will be feeling the temperature because of that flow of air also. Okay, so it means, but that particular situation is fixed to a location. Okay, however the moment, the time, so when you have come from outside to inside, at each instant, at your each location xyz, you have multiple locations when you are coming from outside to inside. At each location time was different, but particularly the time when your location is at door, okay, corresponding to that time you have felt slightly even more temperature because of the momentarily flow of air. Okay, so that is something which is localized to the door. If you will be going at that location, then only you will be feeling the slightly higher temperature. So that term we are calling as nothing but the local temperature. Okay, and whenever I have to explain the total variation, so total variation will be because of the spatial and because of the local. So that is given by this term dt by dt. Okay, so term dt by dt, which is the total derivative, that includes the effect of spatial variation, the convective term, and the local term. Is this point clear? So now basically why I have taken this part first, because one thing we can see that v vector dot gradient of rho plus del rho by del t I can write as d rho by dt. Okay. So now come back to non-conservative form of continuity equation. So in this non-conservative form of continuity equation, now what will be happening? Del rho by del t plus rho. So you can see this term. If you just rearrange this equation and write del rho by del t plus v vector dot gradient of rho plus rho into divergence of v equal to 0, then this is nothing but my local variation and the spatial variation, and these will become d rho by dt. So d rho by dt plus rho into divergence of v is equal to 0. So uh, that is my now continuity equation, but in non-conservative form. So this is continuity equation in non-conservative form. One important point: don't confuse that this is not showing conservation of mass. So ultimately, it is also driven from the conservation of mass equation only. So this is showing conservation of mass, but from the nomenclature of CFD, it is called as non-conservative form. Or in other way, because if I have a fluid element, okay, and that fluid element is actually moving with the flow field. So at every time it is moving with the, so it is not fixed in the flow field, it is keep on moving with the flow field. So if my fluid element is keep on moving with the flow field, so ultimately I can simply write the variation in terms of the total derivative, because it is changing its space and location, okay, with the time. So I can write variation completely in the form of total derivative. Okay, so that is the reason this is also called as Lagrangian form of continuity equation. Okay, now let's try to see the momentum equation. So can you tell me what is the momentum equation in vector form for conservative? Del rho v vector by del t plus rho v vector into v vector equal to minus gradient of p plus rho into f vector. So same thing I will do over here. I will write it v vector dot rho v vector, okay, sorry, divergence of rho v vector and v vector times divergence of rho v vector plus rho v vector times divergence of v vector. Okay, this is equal to minus gradient of p plus rho f vector. So what is this term? First term, okay, one another thing let's do. Split this first term also. Okay, so if I split the first term, then it will be becoming rho times del v vector by del t plus v vector times del rho by del t, then plus v vector times divergence of rho v vector plus rho v vector times divergence of v vector equal to minus gradient of p plus rho f vector. Okay, now so this will become rho v vector by del t. From second and third term I can take v vector as constant, v vector out, that will be becoming del rho by del t plus divergence of rho v vector plus rho v vector into divergence of v vector equal to minus gradient p plus rho f vector. Now the term which I have written in the bracket, can you tell me what is this? The term which is in the bracket. The term in the bracket is continuity equation. How it is total derivative? It is continuity equation. So this term will be equal to 0. Now from first and fourth term on the left hand side I can take rho common. So if I take rho common, then it is del v vector by del t plus v vector times divergence of v vector, okay, and that is equal to minus gradient of p plus rho f vector. So from here this term is now inside the bracket is total derivative. Okay, so this will be d vector by. Now it is very simple to make analogy. So basically uh, from Newton's second law of motion. So what is our momentum equation? Momentum equation is nothing but Newton's second law of motion. It gives the relationship between force and the inertia. So mass into acceleration has to be equal to net external force acting on the body. So for a inviscid flow situation, the forces acting on the body are pressure and the body force. So right hand side is pressure and the body force, and left hand side has to be mass into acceleration. So that we are writing as rho into, if v is velocity, dv vector by dt. Okay, so it means if I am having a moving fluid element whose velocity is given by v vector, then rho dv vector by dt will be its acceleration, total acceleration. So mass into acceleration is equal to net external forces acting on the body. Okay, so this particular form is nothing but non-conservative form of momentum equation. Okay, now let's go to the third equation. So our third equation is energy equation. Now tell me the conservative form of energy equation. What is the conservative form of energy equation? Please tell me. Del by del T of rho times U plus V square by 2 plus divergence of rho into V vector times U plus V square by 2 equal to rho into Q dot minus divergence of P into V vector and plus rho into F vector dot V vector. So this is the conservative form. Okay, so now how to do this? So once again the same thing we will be doing. First and second term we will be actually um, simplifying, and that will become rho times d of u plus v square by 2 by del t plus u plus v square by 2 times del rho by del t. Okay, plus u plus v square by 2 times divergence of rho v vector plus rho v vector times gradient of u plus v square by 2. Okay, and in the right hand side, first term will be rho q dot only, then second term minus p times divergence of v vector minus v vector times gradient of p plus rho f vector dot v vector. Fine. Now, if you see the second and third term on the left hand side, okay, so this is second term, this is third term. So in second and third term, u plus v square by 2 is constant, and inside is multiplier in both the terms. So this can come outside integration, and outside this both the terms, and inside I can have del rho by del t plus divergence of rho into v vector. So means these two terms can be written as u plus v square by 2. This can be taken as common, and inside I can have del rho by del t plus divergence of rho v vector. So now this term inside is nothing but once again the continuity equation. It will be equal to 0, and in the first and last term I will take density outside as common, so on the left hand side. So first and last term on left hand side. So if I take density common, then I will be getting del by del t of u plus v square by 2 plus v vector into gradient of u plus v square by 2, that is equal to rho q dot minus p into divergence of v minus v vector into gradient of p plus rho times f vector dot v vector. So what is this term? Del y del t plus v vector dot gradient. This is nothing but the total derivative. So dy dt of u plus v square by 2 equal to rho q dot minus p into gradient of v vector minus v vector dot gradient of p. So here this is divergence of v, and here it is gradient of v, plus rho into f vector dot v vector. So this is nothing but my energy equation in non-conservative form. Energy equation is an important tool. So this is nothing but the equation of conservation of energy, or I can say in other words the first law of thermodynamics. Okay, so this is an important tool, and it can be written in multiple forms. So one another popular form is, if I don't want over here, say if I don't want over here this v square by 2, so u plus v square by 2 is now the total energy. Okay, so if I only want to write down the energy equation in terms of the internal energy only, u only, I don't want to include the variation of v square by 2. So what I can do, this equation by using some mathematical manipulations, I can write purely in terms of internal energy also. Okay, so for doing that, what you have to do, say this is my equation number 5, and the non-conservative form of momentum equation, say that is equation number 4. Okay, so what I will do, so this is the non-conservative form of momentum equation. So what I will do now, I will multiply this equation number 4 with v vector. So if I multiply equation 4 with v vector, what I will get? I will get rho v vector into d vector y dt equal to minus v vector dot gradient of p plus rho times v vector dot f vector. Okay, so this is my 4 into v vector. Now what I can do, I can actually subtract this particular equation. Say this is equation number 6. I can do 5 minus 6. If I do 5 minus 6, I will be getting rho, and let me split this first term also. So rho into du by dt plus rho into d by dt of v square by 2, okay, and minus of rho v vector into dv vector by dt, okay, and then in the right hand side I am having rho q dot minus p into divergence of v minus v vector into gradient of p plus rho f vector dot v vector, and then this term will be becoming plus v dot gradient of p and minus rho into f vector dot v vector. Okay, so now you can see here this term v into gradient of p, this and these two are cancelling out. Okay, now this term I will try to write in some other form so that it can cancel with the third term. So how to do that? I am say numbering this equation as 7, and particularly I am taking the second term of equation 7. Okay, so second term of equation 7 is rho d by dt of v square by 2. So v square I can write as v vector dot v vector by 2. Okay, so ultimately I can get rho by 2 into v vector of dv vector by dt plus v vector dot dv vector by dt, u into v, derivative of u into v. So from here I will get this 2 times of this, so 2 will cancel out, it will become rho v vector dot dv vector by dt. So now I can write my equation number 7 as, first term is rho into du by dt, second term has become rho v vector dot dv vector by dt and minus rho v vector into dv vector by dt, and in the right hand side I have now rho q dot minus p into divergence of v vector. Okay, so ultimately these two are cancelling out. I am getting rho du by dt equal to rho q dot minus p into divergence of v vector. Okay, so now this particular equation is nothing but showing the variation of internal energy. So this is another important form of our energy equation. Okay. Many times this particular equation is also called as equation of thermal energy. Okay, so internal energy is nothing but thermal energy, so which comes because of the molecular motions. Okay, so what ultimately we have done, equation number 5 was u plus v square by 2. So u plus v square by 2 was total energy. So u was microscopic energy and v square by 2 was macroscopic energy. So this was total energy. Now what we have done some manipulations where particularly the mechanical component of the work, our momentum equation is mechanical thing, force is equal to mass into acceleration. So that mechanical macroscopic component we have multiplied with v vector, so it has become mechanical work. So whenever we have actually removed that macroscopic work from this, then I have got equation as nothing but my internal energy. Okay, so now remember that these two carries the same meaning. So when I am talking about equation number 5, then I am referring to the equation for variation of total energy. When I am referring to equation number, say this is 8, then I am referring to only the variation of internal energy. Okay, so I can use any of the energy equation for my flow field. Okay, so now what you do, so now I will stop. So there are some other things. For example, this equation can also be written in terms of the enthalpy, in terms of